In this video, I'm going to go over the practice problems on simple harmonic motion. Let's look at number 1. In simple harmonic motion, when is the magnitude of the acceleration the greatest? There could be more than one correct answer. So the purpose of this question is to be able to visualize an object undergoing simple harmonic motion, such as a spring. So let's say that it starts when it is stretched, and then it goes back to the equilibrium position, and then it's compressed, then it goes back to the equilibrium position, and then it is stretched again. So this object undergoes simple harmonic motion from here to here to here, all the way up to here. So we're looking for when is the magnitude of the acceleration the greatest. So it's going to have the most acceleration when there's the most force on the object. The force is given by Hooke's law, negative kx. So whenever the displacement x is the greatest, that's when it's going to have the most force, and that's when it's going to have the most acceleration. So if we see that this is the equilibrium position right here, when x is equal to 0, then we can see that it has the greatest displacement at this location. X is equal to a, the amplitude, and at this location over here, where x is equal to negative a, simply because I'm calling any motion to the left of the equilibrium negative. So let's look through the choices and see which of these correspond to these positions of maximum amplitude, where you have the most force and thus the most acceleration. A, when the magnitude of displacement is a maximum. Yes, we just said that. B, when the kinetic energy is a minimum. So when the object is at the amplitude here, we know that it stops because it's turning around, going back in the other direction. So V is equal to 0 at these endpoints. So that means that kinetic energy is a minimum. When the speed is a max, no, that happens at the center at equilibrium. When the potential energy is a max, yes, because the potential energy is given by 1/2 kx squared. So if x is a max, then the potential energy is a max. It's storing the most energy. And E, when the displacement is 0, no, because that's in the middle. That is when x is 0, so there's no force. So the correct answer was A, B, and D. Let's take a look at the next one. An object attached to an ideal spring executes simple harmonic motion. If you want to double its total energy, you could do what? So this is one of these examples where you're doubling something and you have to see what happens. So first you need to figure out an equation that gives us the total energy. So this problem has to do with the conservation of energy section, where we learned that when the object was at its maximum amplitude, such as over here, that the spring potential energy was 1/2 Ka squared, where we just replace the x by a. And then we said, well, if it has this much energy at this position, then that means that anywhere throughout its motion, it's going to have the exact same amount of energy, because energy is not created or destroyed. So we can actually look at this expression as representing the total energy of your object. So now that we've figured out which equation to use, then we can see how do we want to double the energy. Well, we're going to have to double K. K is a spring constant, so the answer is B. We cannot double the amplitude A, because if we double the amplitude, because the amplitude is squared, that means that the energy would be multiplied by 4. Let's take a look at the next one. An object is undergoing simple harmonic motion of amplitude 2.3 meters. If the maximum velocity of the object is 10 meters per second, what is the object's angular frequency? And I actually changed this one for it to read frequency, so let's not look at any of these answer choices. So what we have to do for this one is use the expression that we learned for the maximum velocity was equal to 2 pi f times a. And this came from the equation for the velocity as a function of time, which was equal to negative Vmax times sine of 2 pi ft. This was the equation of motion for an object, a mass on a spring, and we said that this Vmax was equal to 2 pi f times a. So once we realize the equation, this one is a plug and chug. We're looking for the frequency. So frequency is equal to Vmax over 2 pi times a. The amplitude is given here by 2.3 meters. So we just need to plug and chug what we're given. Vmax is 10 divided by 2 pi times 2.3. When we do all this, we'll get for frequency a frequency of 0.69 hertz. So that is the correct answer. I think that was choice B, once I change all of these to hertz instead of radians per second. Let's look at number 4. If a pendulum makes 12 complete swings in 8 seconds, what are its frequency and period? So as soon as you see the word pendulum, you might be tempted to write down the equation that we have for the period of the pendulum, which is the period is equal to 1 over 2 pi times the square root of L over G. But don't be too quick to write down equations that might not be related to the problem, because in this problem, it just tells us how many swings it makes and how long it takes, and you're looking for frequency. So this question is about understanding the definition of frequency. The definition of frequency is the number of cycles per second. So if you realize that that is the definition of the frequency, then all you have to do is say, well, we've got 12 cycles in 8 seconds, so the frequency is going to be 1.5 hertz. And then, if we're looking for period, well, we know that the period is equal to 1 over the frequency. So we just have to do 1 divided by 1.5, and we'll get 0.67 seconds. So this makes sense that if it does 12 swings in 8 seconds, then the time that it takes for one swing is going to be less than a second. It's going to be 0.67 seconds. And that's the definition of the period, the time for one complete cycle. Let's look at number 5. If both the mass of a simple pendulum and its length are doubled, what's going to happen to the period? So I wrote this equation here. It wasn't an accident, because this is the one that we're going to need for number 5, because now it's talking about we're changing some variables and we want to know what happens to the period, and this equation gives us the period of a pendulum. So if we double the length, let's see what happens. This is the original equation, and now instead of putting L for the length, we're going to put 2L. We're just changing that one variable. Notice that even though the mass is increasing, the mass is not in the equation, so doubling the mass has no impact on the period. Only changing the length, or changing g, the acceleration due to gravity, that means if you brought your pendulum somewhere other than the surface of the Earth, then that's what's going to change the period. Let's see what we have left here. 1 over 2 pi. We can take the square root of 2 out, and then we still have square root of Lg. So we can see that the only difference from the new equation for the period, from the old one to the new one, the only difference is that we have an extra factor of 2. The new period is the square root of 2, this factor, times greater than the old period. So the best answer is that it's going to increase by a factor of square root of 2. Finally, let's take a look at the last question. We're given the position of an object that's oscillating on a spring, x equals 18.3 centimeters times cosine of 2.35 seconds to the negative 1 times time. Usually I leave out the units just so it doesn't look so confusing, but this is just a standard unit. Well, it's 1 unit for amplitude. You could also use meters for amplitude. And then this over here, seconds to the negative 1, is the same thing as hertz. So the purpose of this problem is to be able to look at this equation and be able to get some variables out of it. The way to do this is to compare this equation to the standard form of the equation, which says x is a function of time equals the amplitude times cosine of 2 pi ft. This is the standard form of the equation, the wave that represents simple harmonic motion that looks like this. So if we compare this equation, we see that if we're trying to find a frequency, it's going to be related to whatever is in front of the time. What's in front of the time here is 2.35 seconds to -1, but that's what's in front of the time variable. So that means that 2.35 is equal to 2 pi f. So see how we're able to extract some information from this equation by relating it to the standard form of the equation. Now we can solve for f. F is going to be 2.35 divided by 2 pi. When we do this, we get 0.374 hertz. And then the amplitude of the motion, we can see that it's whatever is in front of the cosine term. 18.3 centimeters is in front of the cosine term. So this means that the amplitude equals 18.3 centimeters. So that's it for this video. I hope that this was helpful.